Hello everyone, last time I gave you this problem. You have 4 towns in a 1 mile square. What is the minimum amount of roads you need to connect those 4 towns together? Well, let's look at a few of the possibilities. So we could connect the towns together like this, so every town is connected to every other town. Now each side of the square has length 1, and the diagonals, well, with a quick bit of Pythag, you can work out that the diagonals are root 2, the square root of 2. So altogether, this has length 4 plus 2 root 2. That's about 6.82. We could connect the towns together in a big circle, perhaps. I've already told you the diagonal has a length of root 2, so the circle has a length of pi root 2. That's about 4.44. We could connect the towns together in a big square. That has length 4. Even better than that, we could connect them in that sort of U shape, which has length 3. But it's not a very efficient way, especially to get from A to B. It's not a very efficient way to get around. Perhaps a slightly better answer would be to connect them into a H, which would still have length 3, but perhaps slightly more efficient. But this isn't the minimum answer either. You might have thought the smallest answer would have been a cross. So those two diagonals, well, the diagonals have length root 2, so this has a length of 2 root 2, which is about 2.82. That's certainly the smallest answer so far, but it isn't the minimum solution. Let's find out what is. Working out the minimum length in a problem like this is called calculus of variations and can be quite difficult, but this is where nature is going to help us. I've had a prop made for me, and it's actually 2 layers of perspex with 4 pegs in it, and these 4 pegs are going to represent our 4 towns. And I'm going to dip this into this bowl of soapy water, and what it will do is it will create a film of soap, and this soap film will naturally try to minimize its free energy. So in other words, it's going to minimize its surface area like a bubble. So if I do this, this is going to give our minimum solution. Let's do it. If I dip this in and I'll lift it out, and if I hold this up to the camera, you can see that this is our minimum solution, and it might not be the solution you expect. This actually has length 1 plus root 3, and that's about 2.73. If I tell you that those roads intersect at an angle of 120 degrees, then some of you might like to try and confirm that answer. So let's do this again. Let's do this for 3 towns this time. I've made another prop here for 3 towns, and if I dip this into my soapy water, let's see what answer we get this time. If I hold this up to the camera, you see that I create an extra point there in the middle of the triangle, and these extra points that you create are called Steiner points. And if you want to solve problems like this, they always look the same. They're always 3 roads connected together at angles of 120 degrees. So this was our solution for 3 towns. Our solution for 4 towns looked like this. So this time we have 2 Steiner points, and we can keep going. For 5 towns, the answer is this, and this is the answer for 6. Now for 8 towns, well, here's a solution. This is the internal solution for 8 towns, but it isn't the smallest. In fact, if you connect the perimeter together, the answer is slightly smaller. So the internal solution is just a local minimum. You can think of these minimums as like valleys, and you can sit quite happily in one of those valleys, but it might not be the lowest answer. But to get to the lowest answer, you have to put in some energy first. And we can do this with our soap film. Let's try it out. If I take our 4 cities again, if I put this into the soapy water, if I pull this out in a slightly different way, I've got now a different solution. It's just a U shape, like we've seen before, and this is one of our local minimums. And if you want to get the true answer, you might have to do this a number of times and get a few of these local minimums, and then you need to check which one is the true minimum. But perhaps I can do something about this, because if I take this local minimum solution and blow on it, I now get our minimum solution. This has real-world applications, so if you want to find the minimum length of motorways or building gas pipes or anything like that, even if you had an obstacle that you have to build around, all you need to do is just cut out a section of your Perspex plate there and the soap film will go around it too. It's very clever. And if you have been, thanks for watching.